Okay, yeah, done. Sorry, I just needed to write down the power function really fast. You can scroll down now.
So we can talk about some functions because what we learned so far is y equals to x we learned, right? From y equals to mx plus b. And then y equals to x squared. It's only natural to talk about x equals to, you know, the third power and fourth power and fifth power, this kind of thing, right? Does that make sense?
Yep.
But basically it's coming, this is about the power function. So we can discuss how to draw it though. Of course, in the beginning of the math for human, God knows everything. But for us, we have to draw little by little, right? So basically, draw it point by point is always a good way to learn, right?
Yeah.
So let's just say we did a lot of drawing, and then so this is x squared.
Yeah, the quadratic.
Yeah, and somehow I can also draw fourth power and x to the sixth power, x to the eighth power, x to the seventh power. They are kind of connected. So which means they all look like that.
So the even ones are connected. So the even ones all look like that. Yeah.
Yeah, but what's the difference? You can see that, for example, if this is 2x squared, and if I say x to the fourth power, if I say it's 2, let's say I substitute 2, so 2 this is 4. I substitute to the 4, that's a 16, right?
Yeah. Yeah, it is.
So fourth power, which means it's somehow like this. It's higher, right? Should be here. Right? And then it should be downstairs when it's below 1. Does that make sense? Because when you substitute, for example, if you substitute 1 over 2, this 1 over 2 square is 1 over 4, and here is 1 over 2 to fourth power is 1 over 16. So in here you are a little bit below. Does that make sense? And here you're a little bit higher. Does that make sense?
Yeah.
So the splitting point is x equals to 1. So if I compare this two with let's, do you have decimals with you?
Desmos?
Hmm.
Yeah, I know about Desmos.
So we can see the difference between this. We can draw better than I. So x squared. Wait. Oh, wait. This is two.
Is it x squared or are you doing x?
Squared.
Okay.
And fourth time.
Do you need help?
Oh yeah, you can draw you can do that too.
Uh, just like, well, I would,
You just want to
yeah.
compare 4 and let's say now it's 6 power.
Oh yeah, it gets narrower. I did
if
it
you
myself and it keeps getting narrower and
yeah
like
yeah if you can do it with the calculator, yeah, that'd be good too. So we can compare a little bit.
I just did it with Desmos just now.
So we can compare that a little bit, right? So this is the blue and this is the green. So the higher you get in this way, if you're greater than 1, it's getting steeper, right? Which means it's above. And this part, you're getting a little bit below, right?
Yep.
So seems that's the way to go. And we say the pattern is this is even, right? It's an even number, right? Even number. All even number. Let's
Yeah,
say
the
what?
odd one is like one side is like the odd one is like one side is up, one side is like down and stuff. I'm not sure how to describe it, but the odd one looks like this.
Can you draw it? Okay, good. Yes. All red one. All odd one looks like that, right?
Yeah.
Mm. And then we can go back to the book saying, so you can imagine they have x to the 40th power, but they still look like something like this one, right?
Yeah. I can't really imagine x to the 40th power, x to the 100th power.
Okay, that's a good question. Let's see it. X to the 40.
Oh, it's very square, very rectangular.
Mm-hmm.
Well, not square, rectangular. It's just rectangular.
Yeah, almost. They're increasing so fast and almost they reach to infinity in a second. So, and then this one is odd. So now we can, well, they summarize already. We can take a look at the summary. So this is even. They're symmetrical with y, right?
Yeah.
And domain is pretty much all real numbers.
I think I kind of get it. I think I already know this.
Yeah, so, well, just by the look of the graph that we can know this, right? If you get confused, draw it or do it with the decimal. This is odd functions. Just remember symmetrical with the origin.
I think maybe we can skip the transformations, but I feel like at this point, I feel like I kind of know it.
Okay,
like
transformation we skip.
Yeah, because we did a lot of transformations because we were doing like a trigonometric graph, so we needed to do a lot of transformations. I have to like learn the phase shift and stuff, and like amplitude.
How about zero? If you remember zero. So if x minus r to the m's power is
no,
a
I don't think so. Hang on, let me write that down.
If you're not familiar with zero, then we can
go back there. Go back there. Let me write it down.
Okay. But because that's not the beginning of zero.
I'm familiar with the number 0. Okay, yeah, I just wrote that down.
So the definition of zero is this, actually, to be more exact, is this.
I don't need to write it down again.
Yeah. If you intersect with, for example, if it's this, if you intersect, all this is called the zeros. The zero of this function. Or
wait,
real.
Oh, you just mean the x-intercept? Sorry,
yeah.
I didn't really understand. Sorry.
Yeah. So it's x-intercept, but we
Never
also
mind.
call
Never mind. I understand. Never mind. I understand it.
We also call it zero, right?
Yeah, I know. Other people have called it zero in the past, but I didn't really understand it because it was like zero of multiplicity or whatever.
Yeah, and x minus r is a factor, of course, and the satisfy x.
Can you define zero of multiplicity again? Like, because I think that it's kind of like said like in a fancy way. Because I don't know. It's just like.
Oh, we're gonna get there. The textbook is gonna lead there, and we're gonna get there.
But then why the before the real zero thing?
Well, this is just the real zero definition. So if we only, well, not only. So if we just
no, but I mean, why zero of multiplicity before real zero? If like it needs to be defined later, whatever.
Which means you want to know like zero.
No, just can you define zero of multiplicity in the simpler way?
Oh, well, let's take a look at this example then. Here 2 is a 0 of multiplicity 1, right? So this is 1, right? So negative 3 is a 0 of multiplicity 2 because the power here is 2.
Oh, it's just with the factors of
Yeah,
power
just
up.
the factor.
Okay, yeah, that makes sense.
We have our ways to say it. They just have a way to make it say things probably easier to understand for us or for the computer. Does that make sense? This is 4. We just say the power is 4.
Yeah, that makes sense. Sorry. The definition was just kind of like confusing. It was like x minus r to the power of n plus 1 some factor of x. Like
yeah.
it didn't. Yeah, the definition just worded weirdly, I think.
Yeah. So this multiplicity is 4, and this one is 1 over 2 is a 0, right? You can also say they are all like an intercept, but we also call it 0. And the multiplicity is just as the factor form, what's the power, right? Let's do 6 then. Question 6.
Okay, hang on, let me write this down.
Which one you write down? Example 6?
Yeah, example 6. Are we doing that?
Yeah. You don't write down though. You can just do it on my screen. Can I draw it on my screen? Do the question on my screen?
Oh, yeah. Sorry. I'm just used to taking notes. I forgot about that. Okay, I'm just gonna do all my work. I'm just gonna do my actual work on like I'm just gonna do my actual work on paper for like because there isn't that much space on here.
Yeah.
Wait, I can't write anymore. Huh?
Wait, you can't write anymore?
Yeah, I can't.
Is it okay to write now?
Okay, let me see. Oh yeah, I can. Okay, yeah, I wrote that for number B down. Did it look right?
Yeah, and you can draw it for the question C.
Yeah, could you scroll down? Oh, I guess I could just do it right now. Okay.
I have
Okay,
0,
let me do
0,
that.
2, 2, 2,
Can I do
0.
paper? Can I do it on paper first?
Sure.
Okay, okay. Maybe I can just show. Maybe I can just show it on video. I wrote it down. So yeah, I
Yeah,
don't know.
exactly. You take -1, right? You take
Yeah.
+1 and 2 and 3. Oh, 2 we did it with 0. Sure. Yeah. So it turns out they told us it's a smooth continuous curve. We're gonna learn it in because it's y. And now
Yeah, I
it's
know. I saw that like they did tell us like.
yeah. If that's the case, we're gonna find out a little pattern in here. So it's a 0 of even multiplicity. So that's why we want to bring out the concept of multiplicity more. If it's 0, it touches. So here is the x squared, right? Which means here is going to touch the x-axis. Does that make sense?
Yeah, it touches the x-axis. It's the zeros, the x-intercept, etc., etc.
Yeah. So if it is odd, so there's x minus 1, this is odd, right? Here one is odd, so the multiplicity is odd. So that's why it crossed.
Wait, can you repeat that?
Because the function here saying if it's kind of like if it is a square, you touch it. If it's you know, 1 power, multiplicity is 1, and then you cross that. Does that make sense?
Oh wait, I learned about it. It's like cross or bounce. Okay. So
Yeah.
if R is 0 of even multiplicity, it crosses.
Yeah.
It bounces.
Yeah, it touches, it crosses. And also we can prove it by, you know, drawing a lot of stuff, a lot of like this power function itself. It's checked. And also because we can also prove it by what we learned. See, y equals to x. That's a multiplicity odd, right? And a cross, right? And y equals to x squared. That's a multiplicity even. And then it's the cubic. Well, it's the cube, we know. It's also odd multiplicity. Yeah, also odd multiplicity, right? So it also cross, right? So also prove this is a probably good pattern, right? Is that mean? And this helps us with drawing it. Otherwise, they want to say it's very logical, but if you only do it by point, kind of need more. So we find these 2 patterns, so it helps us with drawing. Yeah, this pattern is already in the calculator, so that's why they draw it fast. One of the reasons. And also, let's talk about near zero behavior. So you basically, we didn't really do a lot of this, right? Well, at least not right now, right? We didn't check with a lot of point like this, right? Does that make sense?
Well, yeah. I think I've already learned most of this, to be honest.
Oh, you learned this? Great.
Yeah.
So what's the
Like the cross, the bounce, some of the actual terms like zero of multiplicity or whatever.
Yes,
It's kind of unfamiliar, but it's kind of, well, it's not unfamiliar, or like maybe I'm just rusty at it or something. But you know, like
yeah. So
it's
now
fun.
what you have, if you learn it, let's just summarize by this. See, because it's what's the original one? X squared, x minus 2. So around this, the near that behavior is negative. Wait, is that 2 times that?
What are you talking?
Yeah, it's more like this one is negative 2x squared. Does that make sense?
Okay, I think.
Do you know this near behavior?
Not really.
Near zero behavior. Oh, we can. As I said it before, we can do it. We should check it with this, right?
Yeah.
So if we check, and then we can find that. Let's just use that table. Here's a little table. If I find it, all this, check it with all this, and I find that this one looks
Quadratic.
almost like this one. See?
Okay. I guess there's such small decimals. Like I don't really get.
Yeah. And also because the other one is just, for example, this one is just so little, so we kind of just forget that. If you time it, some people, why is it negative 2, not x? Because the x, when you get another power, it's so small. Does that mean? So this one and this one are very close. Does that make sense? It's very hard to tell.
Yeah.
So I can just somehow tell myself, because I'm near the like a x squared kind of thing, so it will look like x squared a little bit. Does that make sense? Or negative. Negative 2x.
Sorry, I don't get it.
Yeah, well, if I substitute, I can see the data in here, right? If I substitute again, so they just look very
Well,
similar.
I know, but why? Why do they look similar?
Yeah, it just if I really substitute everything, I should do something like that, right?
Right, yeah, but why?
When I substitute 0, for example, if I substitute 0, and that's a negative 2x squared, right? And why is that one becoming 0? Is because if you really just expand that, it's x cubed minus 2x squared, right? This one is too small. Does that mean? Because you are talking about a small number and then you make it, you time it. So that's why it's very difficult to tell then. Is it making sense?
I still don't understand. Why are we talking? What is this? How? I don't understand.
It's just because, well, if I get all the number, you probably get it. So for example, if I probably use
No,
poly.
I know the number, but like why? Sorry, just continue. Whatever. Maybe I'll get it if like.
It's just because you time as if you, for example, if you substitute 0.0.01, because this number is already small, see? And if you time it another 0.01 minus 2, compare with let's say 0 minus 2, because it's very difficult to tell the first one when you time it to when you time it in here. So basically it's all like just like the rest of like this one.
Well, yeah,
Negative 2 times.
but that's the same fx thing. I understand that, but what does that have to do with y equals negative 2x power of 2?
Yeah, because at that point I don't have to draw everything like this one. It would be easier for me to draw negative 2x squared. So this one, it almost look identical as negative 2x squared. That's why when you near that 0,
why negative 2x squared specifically?
it's
like,
because because you expand that negative 2 times that, and we give up x. Basically, it's this x cubed minus 2 negative x squared. This one is too small. We give up that one up. Does that make sense? Because this is x is already small, right? Around x equals to 0, right? Only because this one is too small.
So we get rid of that by substituting 0 or something close to 0 in there.
Yeah, just near, and that's why we call it near, well, behavior near 0. Is it either you near this 0 or you near that 0 here later?
Okay, I kind of get it.
It's just kind of like this. This one, if you think this one matters, and this one does not matter anymore because this one compared with this one is too small. Does that make sense?
Okay, sure.
Yeah, so that's why we say, oh, well, at this point, I would just do negative 2x squared.
Yeah, I think I understand. Yeah, I think I understand now.
Yeah, this is basically, we're doing it inside the calculator right now, why it looks like that, and whether it's more logical or not. Does it make sense?
Yeah, that kind of makes sense.
So for example, in Google, if I want to go someplace, I said, this is where I'm right now, this is where I want to go. They give us something like this to get there. Now, how exactly they draw it? Yeah, part of it is the function. And how do you draw it like that? And more accurate? Yeah, you kind of need the very small one. But you can't really draw it point by point. That'll take forever, right? So instead of doing that, I just, for example, when I draw this, at this point, I just tell myself as calculator, so just draw negative 2x squared. So he draw negative 2x squared around this place. Does that make sense? To be more accurate, I don't have to go to do all the way, but I can basically copy everything around here. This is called near 0 behavior. Does that make sense? Near this 0.
Yeah, okay. Yeah, it makes sense. So it's like 0, so the x, so like the 3 bit cancels out, but the 2, but if you have the coefficient in front, it doesn't cancel out as much because it's like less 0.
Yes. So in here, then we do another near 0 behavior, which is what we did here. And how about this one? If I rank this is 2, right? So I probably should 1.999 and 1.99, right? This kind of is our rank fits 0, x equals to 2, right? And you can see that this is the actual number, and this is when you use 4 times that.
Yeah, I think I kind of get it. So it's like 0 point. I'm trying to think about this. Sorry.
Does it make sense?
Oh yeah, so it gets closer to 2. So if like x is closer to 2, then like 2 to the power of 2 equals 4. So then, yeah, that makes sense. That makes sense.
So so around this place, I was just telling myself, oh, you can draw 4 times x minus 2.
Okay.
Around this
Yeah.
place. So which means this is why it looks like this. If you draw a tangent line, it would be something like this. Does that make sense? So this is called near zero behavior.
Yeah, it makes sense. Also, can I go to the bathroom for a second?
Sure.
Sorry.
Okay.
Okay, yeah, thank you. 回来了。
All right.
Oh yeah, okay. Oh, turning points next.
Oh yeah. And if we look at the other one, the other 0, which is x equals to 2, right?
Yeah.
If it's the other 0, let's look at this. This is the other 0. How do I know? And this is by, this is the human's limitation thing. You know, we seem to know y equals to the x squared, right? You learned quadratic, right? But actually, do you know that no human, including all ChatGPT and computer, can draw a perfect y equals to x squared function?
That's very hard.
Yeah, it's because when you zoom in, and eventually we are doing estimation because humans can't really touch the area of the infinity. That's one of the reasons. So we basically doing estimation all the time. Although Galileo think observation, more accurate observation, will lead to some fact and truth, but actually now we know basically we can't. We can just do estimation. So that's why when we do x squared times x minus 2, well, basically it's around 2, right? That's why it's near 0, right? If I do 2 here, so approximately 2, I want to do 2 in here, but then in the end, it's just this point. So I don't want to do x 2 in here, so I can do x. So this one I can substitute 2. Does that make sense? Because it's really a range term. And 1.999 squared is really just like 2 squared. Does that make any sense?
Yeah, like x squared, like it does. Yeah, I get it. Like it's getting
So
closer.
any point around that, it's almost like 4, 2 squared,
4
4
times
times x minus
minus
2.
2.
So instead of drawing the accurate one, I can just draw 4 times x minus 2. How do I draw that straight line? That's something that we are better, right? This is called near 0 behavior, number 2. Does that make sense?
Yeah, I think I get that.
So basically what we do is that we get the turning points or maximum and minimum in an example, and then we just find the near 0 behavior. We can basically get the general sketch, right? This is why we do it. And so in the end, I can summarize this. This can, well, the multiplicity can tell whether it's cross or whether it's touch. But the behavior is how exactly you touch or cross, which means it's a 4x minus 2 or negative 2x squared thing, right? Is that again? This thing.
Okay, let me write that down.
Yeah, that's gonna help us to draw the graph.
Okay, yeah, I think I understand. And turning points after this. I think I already learned this. Yeah.
Yeah.
I
So
think I learned
that's
the multiplicity too. I'm just a bit rusty because, like I said, school's over. It's been a while learning curve.
okay. So anyway, so that's why in humans instinct that we know straight line and turning point is kind of a beautiful thing in nature as for eyes. And somehow there's unbelievable beautiful math in there. So turning points. You know turning points? Do you know this theorem?
No turning points. It's like when like the graph changes direction and like.
So at most, if you integrate, and at most you have n minus 2 turning points, right? Do you know that?
Oh, let me write that down.
I mean, if you have n minus 2 turning points, and it's at least n, it's really good. It's just plus 1. 4 turning point, which means you at least 5 power. I mean, 5 degrees.
Yeah, that makes sense because like degree n equals like lots of like, you know, if they're all different, if like there's all like 5 different degrees and stuff, then that's like a bunch of x-intercepts.
Yeah. And the cubic one is like sometimes we draw something like this, right? And the cubic. Oh, actually, the cube.
Oh yeah, that makes sense. That makes a lot of sense. Yeah, I get it.
3 and 2, yeah. So which means there's 1 in between, right? And then we can do example 6, I mean 7. 8. Now we can read 7 and then go to the next page. Which one is a graph polynomial function? Those that list the real zeros and state the least degree.
Okay. Okay. Oh, figure A could not. Figure A could not. Figure B, figure B, for figure B, the least degree would be 5. And what was the other thing that I had to say?
Wait, figure B is 5. Wait. Because you see 2. Are you counting this 4? That's 5?
Yeah, but not.
Wait, we should learn how many turning points.
Sorry, I wasn't thinking about that. Yeah, sorry, that's stupid. Okay, give me a second. Sorry, that was stupid. I was thinking about the intercepts, and then I saw the Martin graph, and I assumed they were just like the turning point.
Yeah.
Okay, 1, 2. Oh, degree equals 3.
Yeah, well, like at least 3, right? To be exact, because maybe something else. With at least 3. Because well, at least you go that far. You never really know what will happen in the future. Maybe there's another thing in here.
Yeah, right? and for number C, the degree is at least 2.
Yeah. So, but also it's a smooth one, so it's probably a polynomial function, right?
Yeah, it is a polynomial function. Sorry, I thought that was obvious.
Wait. C.
Wait,
is C smooth?
Wait, no, I think it has a little bit of like it's kind of sharp near x equals 1.
Yeah. So it's basically not a polynomial function there, right? Because it's not continuous, right? It's not smooth.
Okay.
Somehow it jumped the pattern a little bit. So C is not a function. It's not a polynomial function. How about D? Wait, where's D? Here's D.
Oh, D. I don't think that one has any sharp. I don't think that one has any sharp. And okay.
Yeah. So it's so 1 turning point. 2
I
turning
said 2
points.
turning points. Oh my god.
And that's
I said the degree was 3. Wait, is that a turning point or not?
wait, we have 3 turning points, right?
Oh yeah, sorry, I forgot.
So it's 4, at least 4, right?
Yeah, sorry, I forgot 1. Okay.
So at least 4.
Yeah, sorry, I didn't see 1 because they were really close.
Oh yeah, that is really close. This is the thing, when you zoom in and zoom out, a lot of things have changed, right? So this is one of the reasons. You learned end behavior before?
Oh yeah, I did learn end behavior. Don't worry about that.
Okay. End behavior is compared easy with like a near zero behavior.
Yeah, I've learned most of this. Like.
So how about this? Which one? Example 8. Which one of could be the graph?
Oh, okay. Give me a second. Part 4. those 3 turning points or less. Okay, let me draw the turning point. I think it might be D because it looks like for like the x-intercept is -6, the y-intercept is -6, and like this one looks like -6.
Oh, so this one is out, right?
D, yeah, D.
It must be D, C, D.
Give me a second. Oh my god, what? Okay. Oh, okay. Also, C is out because it has too many. So
Too many, turning points. We can only have like a 3 at most turning points.
B or D, and I think it's D because like here it looks more like y equals -6. I'm doing this by like an approximate scale, but like like assuming like around here is -5, then like this looks better for that. Wait, hang on. Let me think more about this though. I'm just assuming off the scale. Give me a second. Oh, sorry. Oh, yeah. Okay. It's positive, right? So the end behavior should go up. So it's B.
Yeah. So basically,
Yeah, sorry. I'm still sorry. Like I said, I'm still a bit rusty with like some things because end of math, and it took me a second to like make the connection for the end behavior.
Yeah, we're
Maybe we
learning.
should have practiced it a bit more.
Yeah. Well, learn is too fast a little bit sometimes because we learn faster than anything. So anyway, so the point is for any behavior, you just substitute a big value, right? 1,000 or -1,000. You can see where it goes, right? Does that make sense?
Yeah.
Yeah, to summarize everything about graphing, or like a polynomial function is this. So you have no problem with all this, right? This is what we just did in the last 30 minutes. I'm going to move on. How about we can still use this?
Oh yeah, I think we've already kind of done that. Let me write down the summary though, just to be. Can you summarize the end behavior a bit better? I don't.
So for a large value of this, it just well, as I said, you can just substitute 1,000 with the question which is this.
Wait, never mind. I get it.
Right? They said large that it just 1,000.
It's just kind of weird because because they keep using y equals a and x equals n and stuff like that, and it's like what's a and the n and the rest of it.
It's basically either this, right? Or that,
I
right?
get it. Yeah, I get it.
Or that,
it's just kind
right?
of confusing. It's just kind of annoying trying to keep track of all the variables.
Yeah, so for me at that time, we just remember substitutes basically how you learn and behave. You substitute a big number, negative 1,000 or positive 1,000, probably get where you are, right?
Yeah, okay.
And now we can analyze with what we learned from the summary, I guess. Analyze this graph. I mean, if we draw it, how do we draw it more accurately without, using the entire life, our life? How to analyze? What do we know about this graph?
Uh
So how do I analyze this? What do you know if they give you something like this?
oh, okay, yeah. Sorry, I didn't hear you say anything. So
Oh,
yeah, I just thought you were like kind of silent for a bit.
no. I
Okay.
just say analyze here.
Yeah.
How do you analyze it?
So the degree is 3.
Yeah, it means two, right? The most two turning points.
Okay,
Yeah, now we can do zeros. Synthesis.
okay, I'm gonna make the graph really quick.
Sure.
I'm trying to think about this. Sorry, it's taking a moment.
Yeah. So this is called near zero behavior. The behavior near zero.
Oh my god, it shouldn't be like this. I'm trying to think.
Mm. If you can follow the summary, So now it's the time probably for, because this is normally the case, we don't have to talk about it. So now it's the touches or crosses.
I know. This one, I know that it touches or crosses. I'm just trying to think about the rest of the graph as well. Sorry, it's taking. Sorry, let me just do it on my own.
Sure.
5 times negative.
Near zero behavior, you can also call it substitution.
Okay, I think I did it. Yeah, does this look good?
Yeah, kind of. Well, the near zero behavior is also one of the tricky thing here. But as I said I said this one as you can just use substitution 1,000, right? Negative 1,000.
Okay, 1,000. Yeah, 2 times 1,000.
Yeah.
Plus 1.
So you're right
1,
then this is, yeah, like it. And then it turns out we also, if we focus more.
Yeah, if it's odd, then it has like if it's odd, then it has the right is going to be negative and the left is going to be positive, and if there's a negative sign in front of it, then it's like then it's right negative, left positive.
Yeah. And the thing is, if we talk about a near zero behavior, I can still substitute. Let's still use substitutes. This near behavior, it either is n behavior or near zero behavior. I can still substitute. I can just substitute, for example, it's a negative 1 over 2. If I substitute negative 1 over 2 plus 1 and times negative 1 over 2 minus 3, does that make sense? Actually, negative 1 over 2 times 2. If I substitute, this is basically the point here, right? If I substitute that in here, if it is near 0, because this one can be want to be 0, so it can't be. Does that make sense? So I don't want this one to be 0, right? So I'm going to write, instead of negative 1 over 2 times 2, I'm going to write negative, x times 2 plus 1, because I want to keep that. But this one I can, right? Is that here?
Wait, sorry, I don't understand. Why did we get to negative 1 over 2?
It's because you're near negative. You want to talk, because you know that point in here for sure.
Oh, okay.
But
yeah,
you don't really actually know what's, near that, right? So you want to substitute some value in there. But it's basically almost like negative 1 over 2. But when I substitute, I find this one to be 0. That's not what I want, right? So I would just, to be more exact, I would just write negative x times 2. So basically is, not negative x. It's just x times 2. This is negative 1 over 2. So just 2x plus 1 times, but this one and can, right? This one is okay to be, do some approximation. So this is negative 7 over 2, right? That makes sense?
Yeah, okay.
7, 6, 7, yeah. Oh, that's a square, then not anymore. So there's a square there.
Why do you replace it? Why do you replace it with x though? X is like a variable. And
if I don't want to play in x, to be exact, because we skip several steps. So that's why you think this is because if I don't want to do that, I have to substitute 0.-4.9. Does that make sense? Or negative 0.48. Okay. See, if I do that, isn't that just substituting x? Because I don't want to go all the details, right?
I don't really get why you're substituting x, but okay.
Wait, if I don't, I have to do the table. Do you get that? To be exact, if I don't do that.
No, but why do you want these values anyway? What are these for? Like,
wait, what do you mean?
Why do you want these values anyway? They're just close to it, so you know that they're going to be.
No. Because No, you just assume because people before you did that. Otherwise, it's not logical. One of the great things is because it's logical, and you can't really know that. Does that make sense? If you don't do that, you have to do the big table. Remember the big table that we did before? You have to, before we did what, like 1.999, 1.99, 1.9. This, you have to do all that to make sure your graph is, kind of exact. Does that make sense?
Okay, yes.
Yeah. Otherwise, you're just assuming, so which is not what we want, or not what the scientists want, I guess. So anyway, instead of substituting all this, I can just substitute x. Does that mean? So this is 2x plus 1, and so this is 7, right? So that's let me see, make sure I'm right about this. That's negative 1 over 2 times negative 1 over 2. Negative 6. So it's negative 7. So this one is 49 over 4, right? Is that making sense? Let me see, what am I doing my calculation right now? 2x plus 1 and negative 1 over 2. Yeah, I guess this is right. So I can just time it. So this 49 over 2x plus 49 over 4. So which means this one, you're doing that because this one looking like something like that. You know what I mean? I mean this one, this part. Is a little straight line.
Yeah, understood. Like that bit is close to 0.5, so like all the other variables are also going to be.
Yeah, if it is it needs the accuracy, we need this, right? Does that make sense?
Okay.
So this is a near zero behavior. Same thing as the other one. So basically it's substitution. Does that make sense?
Yeah, okay.
So the other one, I would substitute, the other one, x is equals to 3, right? So I would just substituting 3 in. So would it be 2 times 3 plus 1 times 3 minus 3, we don't want it, so we put in x. Is that okay?
Okay.
Because otherwise 3 minus 3 is 0, so we can't
isn't it already like 842? Do I like say an extra? Isn't it already 8:40? Do you have do I just stay an extra few minutes because I joined late?
Well, this is we don't really have this kind of like questions in the exam, but just to be sure to know the logic in there.
Okay.
And we don't ask that much before we did, but now we kind of skip that. We just present the process.
No, what are you skipping? I'm saying what the time is. What are you talking about skipping?
Oh, we just because we kind of had to prove that whether it's like looks like the real graph or not.
No, but I'm saying it's 8:40 and class is over.
Oh, okay. Okay, let me just finish one. So you understand near zero behavior now, right?
Yeah, I understand.
7
it's like close,
x
so
minus
it's close, so
3.
it can basically be effectively you can effectively substitute the value and for like.
It's basically substitute that value or x in there. Is that making sense?
Yeah.
Yeah, and then you can find in like near zero behavior, and then you can get the more exact, more accurate graph. Is that making sense? And how they did it.
Yeah.
Okay, that's it. So the homework would be just let's see. How much time you have? Like how long?
Well, I actually have like an interview right around now, so yeah, I have like an interview for another. I have like an interview for a youth fair, so.
Oh, well.
Wait. Are you talking about like time in the day, like after, not like just after?
We don't have. I think we don't have class tomorrow. We have class the day after tomorrow. So you have 1 day to do the homework. I'm just saying how long you have.
Let me check my schedule. Like 3 hours.
Okay. So then page.
Wait, no, not 3 hours. Sorry, I forgot I have another class, so that would be 5:30 to 5:30, and then let's just give. Yeah, I don't think I have like an hour at most.
Oh, an hour. If it is an hour, then it just you see, this is, let me see which page this is. Why do I see page 185? Yeah, 184. If you only have one hour, then you can see that they have 15 to 26. Yeah, 185, 15 and 26. So for each part, you're doing the first one and the last one if you don't have a lot of time.
Okay, okay, so can you repeat the homework?
15, 26, and 27 and 40. And 41, 48.
Of what section?
Oh, this is only like still 185. Page 185.
Page 185?
Yeah, page 185.
Okay, yeah, thank you.
And then 65, 68, and 86, and 94.
All right, I've got it. Okay, got it. Bye. Thank you.
Okay, bye.